In this video, we're going to talk about how to find the inverse of a non-singular matrix. First, we will discuss the existence of an inverse. Then we'll do a couple of theorems that tell us when we can construct this inverse. And then last, we have a theorem about the nature of singular matrices that have inverses. So we will start with this theorem that talks about the existence of an inverse. So if A is an n by n non-singular matrix, then there is a unique n by n matrix B such that AB is equal to I. And we want to pay special attention to the proof because it is constructive, and by constructive I mean it gives us an algorithm for solving the problem. So the proof starts with A being non-singular because that's what we are given, and by this theorem here it says that if a matrix is singular, then the equation AX equals B has a unique solution for every n by 1 column vector B. So in particular, this AX equals B will have a solution when B is equal to E1, E2, up to En. And just to recall, E1, E2, and up to En, those are our unit vectors. Just some notes here. So E1 has 1 in the first position and 0 everywhere else, whereas E2 has 2 in the first position, 0 everywhere else, and En has 1 in the nth position, 0 everywhere else. Okay, so since AX equals B has solution for every B, if A is a non-singular, that means AX equals E1 and AX equals E2 up to AX equals En has solutions. And we are going to call those solutions B1, B2, and Bn. So the X here that solves for each of these equations, this one that solves for E1, we're going to call B1. This X that solves for E2, we're going to call it B2. And this X, we're going to call that Bn. So what we have then is that we can take all of our column vectors B and put them in a matrix. Then B is going to be our, here it is, B is an n by s matrix whose k column is k, and by the way we constructed it, when we multiply A times B, and remember there's this theorem that says that AB, we can put it in this form where B is in column form. So AB is equal to AB1, AB2, up to ABN. And since each of these we have constructed to be equal to E1, we have E1, E2 up to En, and this is exactly the identity matrix. So this theorem depends both on this theorem here as well as this form of rewriting our matrix multiplication, which we had covered in chapter 1.6. Our first example is to show that A, this matrix here, is non-singular, and find B such that AB is equal to I. So A is equal to 1, 3, negative 1, negative 2, negative 5, 1, 1, 5, and negative 2. And you'll notice that they don't quite call B the inverse of A because we don't quite have all the theorems to prove that I is unique and everything else, but we will get to that later in this chapter. To show that A is non-singular, we want to show that AX equals 0 has only the trivial solution. So here's our matrix AX equals 0. And to solve this system of linear equations, we're going to solve the augmented, or row reduce the augmented matrix. And this augmented matrix row reduces to 1, 3, negative 1, 0, 0, 1, minus 1, 0, and 0, 0, 0, 0, which means that x1 equals x2 equals x3 equals 0. And since AX then has only this trivial solution, we can say that A is non-singular. And we can continue finding the matrix B, which is our inverse. Since A is singular, we know that AX equals E1 has solution, AX equals E2 has solution, and AX equals 3 has solution. So let's look at AX equals E1. We'll start with this one. To solve this equation, we're going to row reduce the augmented matrix, and it row reduces here to this matrix here, which has solution x1 equals 5, x2 equals negative 3, and x3 is equal to negative 5. We are going to name this solution then our B1. Similarly, by looking at AX equals E2, we can find B2, and looking at AX equals E3, we can find B3, and then we can put B1, B2, and B3 into a matrix B, and we can verify that A times B is equal to the identity matrix. And just to summarize this procedure that we got from the previous proof, also just to help us understand the proof better, we started by saying A is non-singular, and by a previous theorem, that means AX equals B has solutions for all vectors B. So that was here. We said A was singular, and we said then we knew that AX equals E1, AX equals E2, up to AX equals E3, they all have solutions, and that's this part here. So the second thing is we set AX equal to E1, E2, and up to EN, in this case, n is equal to 3. We know they all have solutions, so we solved for them. And we labeled the solution for AX equals E1 to be the vector B1, the solution for AX equals E2 to be the vector B2, and the solution for AX equals E3 to be B3, and then we made a matrix from these column vectors B1, B2, and B3, and we found that AB is equal to I, and that was just by design. Our next theorem, which I have a brief name for, which B is equal to A inverse for B constructed from AX equals EN, that's what we did over here. So if A and B are n by n matrices such that AB equals I, then BA is equal to I, and B is equal to A inverse. So we've technically have this theorem that says this will be the inverse. And then this theorem, which is an important one, is the inverse. There's an inverse if and only if the matrix is non-singular. So an n by n matrix A has an inverse B, where AB is equal to I, if and only if A is non-singular. This is a very important theorem to remember. And then to construct A inverse, we use elementary row operations to transform A with the matrix I into I with the matrix A inverse, which is very much kind of in the spirit over here, what we were doing over here. But we'll do an example. So an example of constructing A inverse using this AI transformed to IA inverse, we have the matrix A, which I have told you, given you, that it's non-singular, and it's equal to 1, 2, 3, 2, 5, 4, 1, negative 1, 10. So here is my matrix A concatenated with matrix I. That was this notation here. And it's row equivalent, after many steps, to I concatenated now with A inverse. And I did not do this extra step, but you can verify if you multiply A times this A inverse, that will equal to A inverse times this A, which will equal to I. Our last theorem, so if A is an n by n matrix, then the following are equivalent. A is non-singular, that is the only solution to AX equals 0 is equal to the vector x equals 0. The column vectors of A are linearly independent. AX equals B always has a unique solution, and A has an inverse. So all of these are equivalent. This is another important theorem. This video was relatively short, but we essentially talked about existence of an inverse, and the proof gave us ideas on how we were going to find the inverse, which was the construction. Instructions are right here. There are two important theorems. A matrix A has an inverse if and only if A is non-singular. And then last, these following statements are equivalent. A is non-singular. The column vectors of A are linearly independent. AX equals B always has a unique solution for every B, and A has an inverse. For review, I have two problems for you to try, and I have to warn you, the second one has a little bit of a trick in it, and I do have some comments in the solutions about it. So pause the video, give the problems a try, and then on the next slides I'll have solutions for you. Here's the solution for the first problem. As I had mentioned, the second problem has a little bit of a trick. And if you look at this, so I set this up as A with the identity matrix, and I was trying to reduce it until I got the identity matrix here. And I get kind of close, but you can see in the end, and you can give this a try, you can't get it to be the identity, because here, if I divide this by 2, well, I get a 1, but I can't get rid of the 5, because once I can get rid of the 5, but then then I won't be able to get rid of the 4, and there's no way I can get a 1 over here. So this is just not going to become the identity matrix. Probably the strongest argument is there's no way I'm going to get a 1 back over here. So I can't get it into the form, which of course I thought I'd be able to, but that's because this matrix A must not be non-singular, and so I verified that. So I looked at A, and I tried to solve the homogeneous equation, and you can see there is another solution other than the trivial solution. So A is singular, and so I can't find A inverse. But that does not mean that I can't find solutions for B1 and B2. It's possible that I can. If it's non-singular, that means there's a solution for every B that you want to put into this equation. But that's not to say if it is singular that no B's have solutions. So here, I went ahead and I put in B1, and I went over and I see that this is an inconsistent system. So in this case, B1 cannot be solved. The AX equals B1 cannot be solved, right? And that goes along with the fact that if A is singular, there's going to be some B's that it can't be solved for. But here I put in B2, and you can see I can get a solution, 1, 1, 0, and you can verify that. So this is just kind of an interesting thing. When A is singular, sometimes some of the B's will give you solutions, and sometimes they won't. But when it's non-singular, that's the theorem that tells us that there's always a solution, and you can get an inverse. So that was a pretty long explanation, and almost as long as the rest of the entire video. And that is it for this video. Thank you for watching.